Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is on MCQ and the question is in front of you. I request everyone please pause the video, try by yourself, and whatever answer you get please write in the comment box along with few words as explanation. I believe you have tried, so let's start. Now look at this question. What is the major product of these reaction? Actually this alkyl bromide, I'll say, reacted with alcoholic KOH. What is the major product? Now you can see four options, but before going to details, let's learn a little bit stepwise, because here if you look at stereochemistry is associated, means you can expect okay 3 chiral centers are there. So let's learn a little bit how the reaction will take place and what will be the product. By the way, if you look at alcoholic KOH, remember this alcoholic KOH results elimination product. Reason I shall discuss after some time. Now alcoholic KOH, if I say it reacts with this one, now this structure is pretty confusing, I know, and actually cyclohexane doesn't look like this, because if you look at, you think sir this bond angle is nearly 120 degrees because it's a hexagon, but actually cyclohexane doesn't look like this. Cyclohexane looks like this. Okay, so in this case, now if you look at it, you will be agree sir it is close to 109.5 degree. Now let's number this. This is 1, 2, 3, 4, 5, 6. Do you remember student? Numbering is a very helpful strategy, and I suggest everyone try this numbering. Maybe if you become very efficient, you can do it by yourself, no issue. But if you are a beginner, so I suggest please do the numbering. Now number 1, there is bromine and hydrogen. Now bromine is on the top side, so how can I write? If you look at this cyclohexane, just consider it's a hypothetical line here. So you may consider okay there is a circle, and inside this circle this cyclohexane exists. Okay, so these bonds I am showing, look at these bonds are oriented along the equator, means the imaginary line dissects the planet into two hemispheres, northern hemisphere and southern hemisphere. So that's why these bonds are called equatorial bonds. And if you look at these bonds, so these above, below, so these lines, these bonds are parallel to the axis of this planet. So I mean this, so these are called as axial bonds, these bonds. Okay, and remember this two axial, this one and this one, they are opposite, means anti-orientation. Actually these two equatorial are also anti, because if you try to flip this, I mean this goes this side, this comes this side, so it looks like this cyclohexane. Okay, so whatever bond was here right now equatorial, it will come axial. Whatever this bond is there, means actually if you say this is in equatorial, it will go axial, I mean axial down. So this part, if I say A, this A goes axial down. And what about this one? So if I say this is B, so here this B go here, and if I say this is C, this C goes top. In this way I'm saying. Okay, we'll discuss in some other day, but let's come to our discussion. So here bromine is top, means this is, hydrogen is down, means here. Now carbon number 6, deuterium is down, hydrogen is top. See, in this case this is top, this carbon, so that's why this is hydrogen. Now deuterium down, this is. Now if you look at the carbon number 2, hydrogen is top, so here methyl is down. Now remember elimination, actually this is nothing but beta hydrogen elimination, and beta hydrogen elimination take place in a anti-periplanar orientation or anti-orientation. Now actually it has a reason also. So the bond pair of this carbon hydrogen bond, or in this case you may consider this is CD, should be parallel to the sigma star of CBr bond. Now just look at, this is your bromine. So with respect to this, in anti position, this side methyl group, the beta, so this is the alpha carbon, this is the beta methyl, and this is beta where deuterium. Remember deuterium and hydrogens are isotope to each other, and we know that isotopes have almost similar chemical properties but different physical properties. So what you can expect at this case? So these deuterium will be eliminated. Now when this base KOH, actually alcoholic base, or generally you can consider ethanolic, so this RO minus produced, So it abstract this D. Okay, so this bond pair, I mean here, these can do a overlap with the sigma star of this CBr bond. Sigma star have opposite symmetry, so this is the thing. Now these can do overlap. Remember, any bond cannot made in any way. It's not that much easy, so you need to have proper conformational orientation, and that is obtained in anti-orientation. So the sigma star, which is actually vacant, get electron density from the bond pair produced from the sigma bond of CD. So this pair of electron given or delocalized into the sigma star such that the bond order becomes, actually in this case I'll say bonding electron minus number of anti-bonding electron divided by 2. Bonding electron is sigma, it has 2 electron in the previous time when CBr bond was there, and right now from here one pair of electron goes to sigma star. So you may consider 2 minus 2 equal to 0, so it's a bond order 0. In this way bond breaks. So what it produces, student, let me write. Actually I am not focusing other side, or if you want I can show in this way also. So this is my double bond, and here this is hydrogen, this is methyl down, and rest of the things are as it is. So in this way alkene is produced. So this is the hydrogen. So this is the elimination product. The significance you can see here that the deuterium is consumed and the pi bond is produced. Now next, so this is our product, but here I guess you may have a question. Why the alcoholic KOH results elimination as the major product? Why not substitution? Actually remember one statement that aqueous KOH results nucleophilic substitution as the major product. And obviously SN1 or SN2 depends on the alkyl halide substrate. I mean, as for example, alkyl halide. But alcoholic KOH results in elimination reaction as the major product. Why? Now, when you dissolve OH, means you can, as for example, you can say it's a KOH or NaOH. I mean, I'm saying group 1 alkali. When you dissolve it in alcohol, what happens? This bond, this OH bond is actually polar. This is delta plus, this is delta minus. So as a reversible reaction or equilibrium, this can abstract this proton and it can be RO minus HOH. But from here it will look like, sir, it is not a simple reversible reaction. Yes, it is not a simple reversible reaction, it's a reversible, but equilibrium prefers to remain in this reactant side. Why? Because here if you look at, this is a stronger base, ROH, this is a stronger base compared to this is OH. Actually it is relatively weaker than RO minus. It is also a stronger base, KOH, NaOH, but it is relatively weaker than this RO minus. As for example, you can consider ethoxide, which is a common solvent, ethanol. So from ethanol you get ethoxide, and here if you compare, it's hydroxide. Look at the hydrogen and ethyl group. This is actually the difference here. Now if you look at hydrogen, it doesn't show plus I, doesn't show minus I, nothing. But if you say this is ethyl group, it has a plus I effect, means it donates more electron density to this oxygen. So you can expect this oxygen has more electron density, it is more reactivity, and since it has more electron density, it is more reactive, then it can act as stronger base rather than better nucleophile. By the way, I repeat my statement, if you go to Williamson ether synthesis, you can say, sir, this same ethoxide is acting as nucleophile there. Yes, ethoxide can act as nucleophile or can act as base depending upon the reaction condition. In this case, student, if you take alcoholic KOH, then it produces this alkoxide, is the anion intermediate, and it is more reactive. It is stronger base, that's why it reacts, and under this reaction condition, elimination gets preference over nucleophilic substitution. Because remember, as I told, stronger base prefers elimination over substitution, point number 1, and here bulky base prefers elimination over substitution. What do I mean? If you look at this hydroxide, here hydrogen, very small atom compared to ethyl group, so from there you can say, okay, this is less bulky, so this prefers substitution. Okay, but if compared to this ethoxide is more bulky, so it prefers elimination. Even as for information, remember, potassium tertiary butoxide, Okay, it is a very bulky base because 3 methyl groups are there, so it is a best choice for elimination reaction. Okay, fine. And remember, better nucleophile is actually less bulky, as I told in this case of KOH, and this prefers substitution over elimination. This is a very important concept. I believe you have learned. Now, according to our discussion, what is our answer? Answer is option C. No deuterium there, alkene, and next position methyl. By the way, this is also asymmetric, but I have not mentioned in the problem, so you don't need to be worried about. Now, if you get this question less than 30 seconds, how can you solve? What is the major product of this reaction? In this way, you need to understand that, okay, first, alcoholic KOH. Elimination is the major product. I asked major product. Fine. Now, where the elimination student, many students try the tricks. Okay, this bromine top, what is the bottom? Methyl cannot eliminate. This deuterium. Okay, from there go. If you do, you'll get the right answer. But student, I generally not recommend. Try to remember or try to visualize the cyclohexane original structure which I have shown here. I mean this one. It is very helpful. Okay. Now, if you get this question in the exam hall, how can you solve it less than 30 seconds? Alcoholic KOH elimination reaction. That's we know. So what is the option B? It is a nucleophilic substitution. Eliminate instantly. Okay, so this is gone, and it's a secondary halide, so anything should be written about the stereochemistry I have not mentioned because it follows a mixed kinetics, very confusing. So okay, this is not possible, nucleophilic substitution cannot take place. Now next point, okay, elimination. So elimination can happen where these hydrogen, these bromine, same site as I drawn. I suggest if possible quickly think or draw this structure in your mind, the cyclohexane structure you can easily get. So from there you can get one thing, okay, according to this elimination, that okay, these or these possible. Now if you look at bromine and hydrogen top side, elimination, seen elimination there, but KOH, alcoholic KOH mediated elimination is an anti-elimination. So here it is not possible. So option A is also gone. Now between option C and D, for that purpose, same logic, seen side, so elimination not possible. If you ignore this one, obviously you should ignore this one also. So what is remaining? Bromine, hydrogen, deuterium, anti-orientation, and 1 point isotopes of similar physical properties but different chemical properties. So from there also you can conclude, okay, they will remove. So option C will be the right answer. It is easy, but it is little confusing. If you do little more practice, you can solve it quickly, and I guess that will be helpful for you. Thank you for watching this video, and if you really enjoy the content of my channel, please help this channel to grow. And regarding any doubt about the logo of my channel, please read this part, your doubt will be clear. So see you in my next video. Bye bye.